let us recap what we have achieved so far. We were discussing trigonometric functions and pi. We have so far shown that if 0 is less than or equal to x less than pi by 2, we have 0 is less than or equal to sine x is less than 1, and 0 is less than cos x is less than or equal to 1. Okay, and we also have sine pi by 2 is 1 and cos pi by 2 is equal to 0. We have these identities. Furthermore, we have also proved identities for sine a plus b and cos a plus b, the addition formula. It is immediate by applying the addition formula, we get additional identities. These identities, let me just list a few of them and you can spend a nice afternoon proving all of these. Number 1, sine pi is 0, cos pi is minus 1, we have sine 2 pi is 0, and we have cos 2 pi is equal to 1. Okay, let's say you want to prove one of these. Well, you just look at sine pi. This is just sine pi by 2 plus pi by 2, which by the addition formula will immediately give 2 sine pi by 2 cos pi by 2, which is going to be 0. Okay, and you can prove all of these identities in quite a similar manner. These are just elementary stuff which you have no doubt seen in your high school. Okay, also we have some more identities which I'm just going to list and leave you to prove it. They are all familiar identities that you have seen in a high school, and the proofs are exactly the same. So we have sine x plus pi by 2 is cos x. We have cos of x plus pi by 2 is equal to minus sine x. We have sine of x plus pi is minus sine x. We have cos of x plus pi is minus cos x, and we have sine of x plus 2 pi is equal to sine x, and finally we have cos of x plus 2 pi is equal to cos x. Now these are various trigonometric identities, all of which follow immediately from what we have established and the addition formulas. They're fairly straightforward to see. Okay, now we are interested in the shape of sine and cos. Let's see how we can derive the shapes roughly of sine and cos using what we have derived. Well, we already know that d by dx of sine x is cos x and d by dx of cos x is minus sine x. Okay, now let's focus on the interval 0 less than x less than pi by 2. In this interval, cos x is greater than 0, right? Therefore, what we can conclude is that sine x is strictly increasing in the interval 0 is less than or equal to x less than or equal to pi by 2, simply because the derivative is greater than 0. Exactly in the same way, we get that cos x is strictly decreasing in this interval. Okay, so we know that in 0 to pi by 2, sine x is strictly increasing from 0 to 1, and in a similar way cos x is strictly decreasing from 1 to 0. Okay, now we can repeat using some of these formulas involving sine of x plus pi by 2 and so on. We know that if you take pi by 2 less than or equal to x less than or equal to pi, we have not shown, you will show that sine x is cos of x minus pi by 2. Okay, so that means in this interval sine x strictly decreases from 1 to 0. Okay. Whereas cos x is strictly decreasing from 0 to minus 1, because the derivative is minus sine x, which will be less than 0 in this interval, which is what we have established right now. Okay. So similarly, for the interval pi to 2 pi, we just use the relationship that sine x is equal to minus sine of x minus pi. And with this we can derive rough pictures of the sine function, and similarly for cosine. Similarly for cos x. Okay. So what we do is, roughly the picture for sine and cosine is going to look like this. This will be sine x and this will be cos x, roughly. So this will be pi by 2, pi, 3 pi by 2, 2 pi, and similarly pi by 2, pi, 3 pi by 2 and 2 pi. Okay. Now you notice just from the data about the values of sine and cos at these various points and the fact that it's increasing and decreasing, I am drawing a picture that looks like this. So let me highlight that in some glitter pen. It looks like this. Okay. That comes from convexity. That comes from convexity. Recall that when we had studied derivatives, we studied convex upwards, convex downwards, and so on, right? So the convexity properties are obtained by considering the second derivative. Okay. So what I urge you to do is compute the second derivatives in each of these intervals and look whether the second derivative is less than 0 or greater than or equal to 0, and try to see that the pictures have to look like the way the curving is going on has to happen in the way that I have described. So once you have the values of sine and cosine and whether it's decreasing or increasing in the various intervals, and also the fact about the convexity, you can get a rough picture of sine and cosine, and it's going to look exactly the way you expect it to look. This is a course on real analysis, and you have just watched the module on the shape of sine x and cos x.